I'll be explaining over the code. So our data set was, it's called an Epicurious recipes data set, and we got it from Kaggle. So the project is based around the Epicurious dataset, and it consists of over 20,000 recipes listed by recipe rating, nutritional information, and assigned category. So what we mean by that is, so we have a title column here, and each row in the title column represents a particular recipe, right? And the nutritional information that's represented are in the form of other columns. So we have calories, protein, and fat, and there's also a rating for each column. I mean each recipe, right? So and yeah, and the remaining everything else is whatever, either it's the ingredients which are part of the whole data set. So we have about we have the total column list is about 680 columns. So the ingredients are the major part of our data set, which form the columns, and these are the ingredients column are binary in nature. So let's say one of these ingredients are present in the recipe, so it'll be 1, else it'll be 0. So basically this column right here, this ingredient isn't present in these these 5 recipes that we're seeing, right? But our calories, protein, fat, and sodium are all continuous in nature. The data set is continuous, and a rating is also continuous up to say 5. So from 0 to 5 it's continuous. So yeah, and yeah, so this is our data set. If we have to show, so there's a whole lot of rows, I mean columns, and about 20,000 rows. So there are 680 columns, right, totally. And we can only focus and do analysis based on these, because these actually mean something, right? The ratings, the calories, protein, fat, and sodium, and the remaining we had to like run a code for it, and we had to feature scale it and feature engineer it, and we couldn't go over them manually. So if we check the information of our data set, we see that there are 20,052 entries and about 680 columns, right? And describe, this just shows the, yeah, this is not like that relevant right now. And rating, see, or if you could see the rating column for describe, we can see that the max rating is 5 and the minimum is 0. So it varies between 0 to 5, and it's continuous in nature. So now there was our analysis part, right? So what we did was we had to check the number of null values in. So a primary column, what we could focus on was calories, protein, fat, and sodium, and rating, right? So we had to deal with the null values. So yeah, we can see that there are over 4,000 null values in calories column itself. So what we've done is, here we're basically including only those rows which have calories less than 10,000, because that makes sense, right? We assume that each recipe is for one person, one serving, and anything over 10,000 is probably an outlier and is not relevant. So we did that, and we included, and this code, usually if we don't include this, the null values get removed, and we didn't want to lose that data. So we wanted to keep the null values and only those calories that are less than 10,000. And after doing that, we calculated the mean, and this was the mean, and we filled the null values with the mean, right? And now you could see that the minimum is 0, and yeah, the mean is so much, and yeah, some of the rows were removed, and the max were less than 10,000, about 9831. So this was like what we did for calories, and we move on to the data analysis part. So you can see that this is the rating data analysis. This is data visualization part, and this is the graphs we obtained for a histogram plot for rating, and you could see that it's left skewed, right? Most of the rating is concentrated between somewhere between 3.5 to 5. So we have a few outliers here, and this is another box plot where you could see that the quartiles are between everything, or most of the data is between 3 to 5, and we see outliers here, right? And rating didn't have any null columns, I mean null rows, so that was fine. And this was how our calories were skewed, right? It is right skewed here, whereas our ratings were left skewed. So most of the calories were between 0 to say 2500, 3000, right? So, and this was how the box plot was. There quite a few outliers in calories, and this is our rating, just like a density plot sort of thing. And this is for the calories, right? And we did a scatter plot again for calories to see that was it actually necessary to include anything above, to see how they're again scattered all over the place. But mostly they're within, most of the data is within 4000, right? So yeah, and we did a pair plot to see, just to observe rating and calories. And this is just our data set again, which where you can see that, you can see clearly see that these are binary and these are continuous in nature. And yeah, so this is what we did. Since we know that yeah we have too many columns to deal with, and what happened was, when we observe a few columns, there are some columns which don't make sense, like they're not even ingredients, and we knew that there might be some dirty data available which don't make sense. We assumed, and for our analysis it was necessary that these columns are only ingredients, right? So what we did was, we just written a hard code over here where which removes all the columns which are that are present in less than 10 recipes, right? So only the columns which remain after this have to be present in at least 10 recipes. So that removed some unwanted stuff, like, see, Alaska and Aspen and Atlanta, Australia. These aren't like recipes, I mean ingredients. So that got rid of about over 150 columns, right? Okay, so here we tried to kind of like have a meal plan where people can find lunch, dinner, and breakfast dishes and create a meal plan for them, right? So these are some of the code we wrote to just like give out sampling. So here there's a row number, and probably we've broken down the data set into lunch, dinner, and breakfast. And when you do the sampling and sample date sample, like, you take out a row, you're getting breakfast cookies and herb cheese and zucchini omelette and something like that. So that would be for lunch, and this is for dinner. So these find the vegetarian and non-vegetarian dishes in our data set and compare the calories, basically, right? So you can see that non-veg dishes don't have too many. There are not many dishes in under non-vegetarian that are over. I mean, under vegetarian that are over 2000 or even like 1700, right? And yeah, apart from that, they're pretty much identical. So this is just a side-by-side comparison of non-veg and veg calories. And you could see that the orange clearly indicates non-vegetarian, as seen in the above graph as well. We have dishes that are over 2000 calories in under non-veg, right? Okay, so this was just something we tried out to see if there's something interesting, some interesting pattern or something that we could, this is just like to extract something with our data set because it seemed interesting. So this is where actually our most of the analysis begins. So we first did a correlation matrix to just see, because since these are our primary columns, we just wanted to see if we could do, when this we had to do some sort of prediction with these, right? So and we had to like check out the correlation. So we initially had rating as our target in mind, but and since the remaining columns that we have are ingredients, they actually have some sort of like statistically they must be related to calories, protein, fat, and sodium, because these columns data is directly related to those ingredients, right? So we wanted to mainly see if rating has any correlation with calories, protein, fat, and sodium. So as you can see, rating really doesn't have that high of a correlation with calories, protein, fat, or sodium. But what we see is calories has good correlation with protein, with great correlation with fat, and about like you could see some correlation with sodium, right? So that makes sense as well. Calorie is basically composed of protein, fat, and sodium. So this was our initial finding that rating might not be related to any of our other columns, and it's hard to find any correlation or any statistical analysis because ratings is continuous, and those other columns are binary in nature. So this was our initial finding, and we moved on to hypothesis testing, where we checked if our data set is normally distributed, right? So this is for rating, and we did both the Shapiro-Wilk test, the K2 test, and the Anderson-Darling test, and we replicate these tests. I mean, we apply these tests to rating, calories, protein, fat, and sodium, and yeah, so we run the code, right? And this is where we're doing it for. So rating isn't normally distributed. We could see p as 0.00 does not look normal, and again p value of less than 0.05. So rating isn't normally distributed, nor is calories. Again, we're getting a p value less than 0.05. It's all zero. Probably if we adjust the sensitivity, we might get some value out of it, but as of now, we can see, and even we apply the same thing for proteins, it's not normally correlated. After the normality tests, we kind of had the assumption and almost like another hypothesis that so calories has the calories column has good correlation with protein and fat, right? So we tried to use the Pearson R correlation test. Since it's not normally distributed, we weren't able to use the Spearman rank correlation. So we had to use the Pearson R correlation, which is one of the factors. So it has to be normally distributed for us to use Spearman rank. So since that wasn't the case, this is void anymore. We can't use it. So we had to use the Pearson R correlation test, and you can see between calories and proteins we have something almost 0.7 correlation, which is pretty good. And then to check between fat and calories, we had to fill fat again with fill the null values of fat again with its mean. Now it has no null values anymore, and yeah, we use this and find the correlation with calories, and you can see it has pretty high correlation of 0.9. So it's something we could use for our analysis, and so this all of this is again part of our feature selection. And yeah, so right now we assume that calories, so right now we got to know that calories is is good, it has good correlation with proteins and fat. So if you could wish to just get another proof of that, when you visualize it, you see that you can draw a regression line, and that pretty you can see the correlation, and that's more evident in calories and fat. But when we see calories and sodium, sodium was another nutritional column of ours, there's no correlation, right? I think it's redundant. Yes, there's no correlation. And just to like enhance this visualization that we have done here, we try to implement a code which draws a regression line. So you can only make sense of these graphs only when there's a regression line. So we've written this code over here. So it takes two inputs basically. Yeah, so it takes two inputs. We can either take the basically numpy array values of two columns, and we can pass it to the function. And then when that happens, what we see is a regression line. So when we take fat and calories, for example, here the same graph over here is drawn with a regression line to get a better understanding of the correlation and kind of understand that this can be part of our features to predict calories. and this is protein and calories. So yeah, so basically the y-axis is calories here as well. Y-axis is calories, the dependent variable. So you can see that even though it's not as good as fat, it's still, usable. It's pretty good, and we can use it for our analysis. And then again, sodium and calories, there's no correlation. I don't think, I mean, it's evident, but we can't be using this. It might give us an error. And just in case, to see what's happening here, we tried to see if rating has any correlation with any of them with while using the regression line, and as you can see, there's nothing here, neither with calories nor with proteins. So yeah, and what we tried to do, one more thing, was like to standardize rating with the other features so that they're all in the same scale, and try to do some regression analysis with it, right? But even the standardized, so we use standard scalar over here to standardize our rating, because it might be that the dimensions of rating and the magnitude of rating to something like calories, protein is very off. So one more thing which hit us was we could try standardizing the features, standardizing the rating column with the other features so that they're all in the same scale, and we can try visualizing it and understanding the correlation. So we use standard scalar, and yeah, we transform the rating and protein, for example, here, right? So basically rating and protein after standardizing it, and again we pass it through that function, and then again there's no hope, there's again no correlation. So all of this was part of our feature engineering process, and yeah, after the data cleaning and after our data cleaning, we kind of figured out through all these steps that rating isn't particularly useful for us. It's not useful for us in any sense, and at least because it's not doesn't show any relation with the nutritional information, and the nutritional information indirectly makes up the mass of our data set. Even though the columns are ingredients, the mass of our data set consists of ingredients. Those ingredients add up to nutritional values, right? So if the rating column is not related to our nutritional information, there's no point of using it, and it won't make sense. So we had to drop that, and the thing we could use right now was only calories, protein, and fat. So that's how we moved ahead with our ML model, machine learning model, where we had to keep the calories as the target, the protein and fat as our features. Okay, so yeah, we just like transforming our data set in that regard. We had to drop the rating column, and obviously the title column, which is not useful and can't be used in prediction. So this is the data set we get, and again we had to pre-process it, and we use standard scalar over here to normalize the calories with protein and fat, so they're all in the same scale. So this is what we get right after normalizing it using standard scalar again. And yeah, I just take x. So x here represents my features, protein and fat here, and y represents my target, and we import train test split, which is standard across, and we split the data set into training and testing data set using the acceptable 0.3, I mean 30% as our test size. So I mean, before, even though in the order we've implemented SVR and random forest regressor, I'd like to go ahead and first explain linear regression and regularization. And because linear regression is just vastly used, and it just makes sense to anyone would first go for linear regression for any regression analysis. So yeah, so linear regression, we perform the same thing. We had to normalize it and get it to scale, and again train test split, and we had to split the data set, and we used sklearn model itself for linear regression. And you can see the coefficients and the intercept, but then again you can see all the scores over here, the accuracy score. So we used r square value standard across all our ML model to compare the results. So here we see the r square value is giving us 87.86, right? 87.86 accuracy. So that's pretty good, but then again, we don't have any reference, so we had to move ahead. And we know the limitations of linear regression, right? The assumptions it makes, and part of using linear regression is, again, we know that when we did perform our regression analysis, this part, we know that these two are linearly related. That means fat and calories are linearly related, and protein and calories are linearly related. So we had to go for linear regression, and or any other regression analysis we use, we had to set the kernel, or even the way the prediction is made, to set it to linear. So even in linear regression, we use linear regression, and as I said, we got an accuracy score of 87.86. But then we know the assumption made by linear regression. So it's like the independent variable should not be correlated, and there should be linear additive relationship, stuff like that. And like the stuff like error variance must have constant. I mean, the error terms must have constant variance, and these sorts of assumptions lead us to other algorithms. But before that, we had to do regularization. Regularization is, again, to avoid overfitting, right? So that's one of the reasons why we use linear regularization. And so here again, we can't just assume linear regression would give the best result. So we have to regularize it using, and we have two processes. We can either use ridge regression or lasso. I've tried both. We've tried both. And so then again, here, this is what we've used for ridge regression, and we get the same, almost the same accuracy as linear regression, which is 87.86. But lasso gives a worse accuracy of 86.6. So basically, ridge and linear regression have the same accuracy, and that was good. But then again, we tried to move on to more sophisticated algorithms, such as support vector regression. We can't use support vector classification, and if we use support vector machine, we had to go for the regression stuff, since it's regression analysis. So what happens here is, then again, we tried so initially, if you have to explain something, we did use just import SVR instead of linear SVR, and we use grid search CV to optimize the parameters. And there again, we got C as 0.1. Even the code is not present here. The grid search CV gave us that by setting the kernel as linear, and it gives the C parameter the best accuracy for 0.1. So we use the same thing, and we use C as 0.1, and we directly imported linear SVR, because the regular SVR, by setting the kernel as linear, was taking too long for our data set. And SVM is known to not handle large data sets very well. So we had to directly use linear SVRs for the computational speed only, and this gave us an error of, accuracy of 87.5, which is a little less than linear regression, surprisingly. So, but we had to accept it. And yeah, this is, again, we just want to try random forest regressor, being the bagging technique, the ensemble technique. We just wanted to see, because it's known to handle large data set and find quicker correlations, and it's a bagging technique. It uses multiple decision trees, so it must be of some use, and it might give us some interesting results. So we tried the same process by importing random forest regressor from sklearn.ensemble, again showing it's an ensemble technique. And random forest regressor gave the least result of 85.355, which was pretty surprising. And yeah, this is what the prediction we could do, and this was the accuracy we got by predicting the calorie value using protein and fat. project was, and to predict calories, and as we could see, ridge regression, basically linear regression, which with ridge regularization gave the best results. To conclude, and so what we tried to do again was to try and implement something else with the rating column. I've just opened another notebook here. Um, we wanted to see if we could convert rating column to nominal data and see if there's any correlation, because anyway these are binary, so we could find some correlate. It would be easier to correlate data with rating column now that it's nominal. So what I did was what we did was we took any rating value below 3 and made it 0, implying low rating, and any rating value above that as a high rating, and we converted the whole thing to binary values, and then we find the correlation with the whole data set. I just applied the whole data. We just applied the whole data set to find the correlation, and so this is the variable, the correlation matrix over here. But then when we find the correlation matrix for, so I just so this variable basically stores all the correlation matrix, basically stores the correlation of the rating column which is greater than 0.4, which is like decent correlation. So when we find the value counts, there's only one column that has correlation greater than 0.4 with the rating column. So that didn't again provide us with any results that we could have used for any prediction with rating column. And yeah, I tried the same thing with making it into mean, like making it nominal by using the mean as the threshold, mean of rating as a threshold, but then again didn't work. And here was another thing we tried was, since all of these are column names, we basically made a new data frame which basically takes all the recipes as rows and the count of the ingredients. Basically all the columns that are present is under this ingredient column over here, and it has the count, the number of ingredients present. We wanted to see if there's any correlation we could find. So using that data set, uh, yeah, we did this pair plot and stuff. You could see that ingredients and something like calories has a correlation. So that makes sense also, that ingredients increases, calories increases, but we couldn't find anything with rating. So yeah, and ingredient increase, even protein, it had good correlation with protein and fat as well. The ingredient column. When we say ingredient column, I'm referring to this, basically the count, right? But yeah, we couldn't use that in any. It was just nice to observe and make an assumption and understand the data set and the whole point of this data set, but we couldn't proceed with any further prediction or analysis with that. So this is the end of it. Thank you.